Welcome to the first lecture in physics this year. This corresponds to section 1.1, Mathematics and Physics in your physics textbook. The expectation is that you'll watch this lecture and copy the notes into your composition book to use later as you work through the problem set in class. Further, feel free to read the textbook for any additional information that you might need to understand the concepts covered in this lecture. We have 6 concepts that we're going to cover during the course of this lecture. Each of them are not, we don't have to go very far in depth to any of them. They're pretty quick, but there's quite a few of them. We're going to talk about physics and what it is. We're going to talk about the use of math in physics. We're going to talk about the regularity of the SI units that we'll use throughout the course. We'll talk about dimensional analysis as a method to relegate derived units. We'll talk about significant digits, what that means, and also very briefly about scientific methods. So what is physics? Physics is simply the study of the natural world. Physicists seek to quantify, to find formulas that explain how things in the real world work. That could be electricity, that could be forces, that could be gravity, that could be magnetism. Anything that we can observe on Earth, we want to be able to explain. Now, math is the language of that explanation. Physicists are always looking for formulas that have the ability to explain what is observed on the Earth. You'll start to use some formulas today, but without a toolbox of formulas, they'll be very simple formulas. For example, let's look at this formula that you're asked to use in your problem set. This is Ohm's law. Ohm's law states that in an electrical circuit, voltage is equal to the resistance times the current in the circuit. So you might get a problem such as this. If a 9-volt battery encounters 100 ohms of resistance in a circuit, what is the current? Now, you've done problems similar to this in the past. Most of you probably know that you need to plug the 9 in for volt and you need to plug the 100 in for the resistance. In fact, there are 2 ways to solve this problem. One that's been okay in the past and works, but isn't exactly what we're looking for in a physics environment. On the left-hand side, you see kind of the plug and solve method of solving this equation. Like I mentioned before, if you plug 9 in for the voltage, 100 in for the resistance, you can solve this algebraically for the current. The preferred method in physics, though, is on the right-hand side. What I would like you to strive to do in your problem solving is to solve for the variable that you're being asked for the quantity of, in this case, current, before plugging any numbers in. Either way you go, you'll arrive at the same answer, but by solving the equation algebraically first, you limit the possibility of making a mistake in calculation. SI units are the agreed upon standards of measurement in physics. These are the units that physicists across the world have agreed will be used to measure certain quantities. Now, SI units come in 2 different flavors, base units and derived units. The base units are the building blocks for all of the measurements we will take. These are not your common English measurements. They're instead the metric measurements. For example, length in this class will always be measured in a meter or a prefix of a meter, and the symbol for meter is M. Mass, which is different than weight, and we'll talk about that in future lectures, is measured in kilograms. The prefix for kilo is K, and the symbol for gram is G, so kilograms is kg. The SI unit for time is the second, which is really about the only measurement of time. It's represented by the symbol lowercase s. In this course, we will encounter many derived units. One derived unit is the Newton, a measurement of force. Notice that the Newton is defined in terms of base units. So here the Newton is kilogram times meters per second squared. Another derived unit that uses the base unit is velocity. Velocity is measured in meters per second. Again, notice that we've used 2 base units to create a new derived unit. Because we will deal with small numbers and large numbers, it's important that you are reminded of your metric prefixes chart. Here is a sampling of some of the prefixes that we will use in this class. Notice that we start as small as 10 to the negative 6, which would be 1/1,000,000th of a base unit, micro. The symbol for that is mu, the Greek letter. The rest of them you are probably familiar with: milli, centi, kilo, mega, giga, and tera. In this lesson, you'll be asked to convert from one prefix to another. The key to remembering this, or the key to being able to do this, is to remember this phrase at the bottom. When we go up the chart, we move the decimal point to the right. As we go up the chart, the units get smaller, so the number gets bigger. When we go down the chart, we move the decimal point to the left. The number of units that we move the decimal point is equal to the difference in the exponent of the scientific notation. So if we were asked to convert from 1200 centimeters to the equivalent number of kilometers, we would notice that centimeters is -2, kilometers is +3, the exponent on the scientific notation. So we would have to move the decimal point 5 units. -2 to 3 is 5. Since we moved down the chart, we'd move the decimal point to the left. So 1200 centimeters is equal to 0.012 kilometers. Dimensional analysis is a technique that gives people trouble, but it's really a very simple idea. When we want to relegate derived units to an answer, sometimes we have to do multiple conversions. In this example, we're being asked to convert from 43 kilometers per hour to the equivalent number of meters per second. That requires several multiplications and several divisions. Dimensional analysis allows us to set these up as fractions and work from one unit to the other. So notice at the far left, we start with what we were given, 43 kilometers per hour. And at the far right, we have the units that we want, meters per second. There's multiple cans in this problem, but if you'll notice, each one of them is equivalent to 1. The first fraction to the right of 43 kilometers per hour is 1,000 meters. Well, it's over 1 kilometer. We know that 1,000 meters equals 1 kilometer, so that fraction is basically 1. Why in the world would we multiply by 1,000 over 1? Well, it's because the kilometers will cancel out. Kilometers divided by kilometers is equal to 1 as well. So now 43 kilometers per hour equals 43,000 meters per hour. We still have a problem with the hour though. So we know that 1 hour is equal to 60 minutes. If I multiply 43 times 1,000 and divide by 60, now I'll have my derived unit in meters per minute. I know that I need to go to seconds, so I multiply again, this time by minutes over seconds. The minutes cancel out, and I end up with my desired unit, meters per second. So to do this problem, I take 43 times 1,000 divided by 60 divided by 60. I would end up with 12 meters per second. You will probably struggle with dimensional analysis as you first encounter it in your problem set. Please ask questions and let me walk you through this with another couple of examples to cement the knowledge. Another concept covered in this section is significant digits. Physics is different than math. In mathematics, we add two numbers together and we write down whatever the calculator punches out. But in physics, we're more concerned about what the actual measurements say about the final measurement. In this case, we will cover significant digits more as they become necessary throughout the coursework. But the key point is to never report an answer more precise than the least precise number. So taking the first example, 4.534 centimeters plus 3.2 centimeters, 3.2 is the least precise number. So when we plug this into our calculator, we get 7.734. Well, the 3 and the 4 just don't mean anything because our second measurement wasn't made to that precise of a measurement. So because 3.2 has only 2 significant digits, we round our final answer to 2 significant digits, 7.7. And actually, I should say, place us past the decimal point, because if that was 0.32, that would change how many places we went past our decimal point in the end. The least precise number is rounded to the nearest tenth of a centimeter, so we have to round our final answer to the nearest tenth. You'll notice a similar problem below. That one, 139 centimeters times 2.3 centimeters, because the measurement on the left is only measured to the nearest centimeter, our answer can only be reported to the nearest centimeter. Your answers will be graded according to this, so don't blow off this idea. You need to round your calculations to the least precise number involved in the calculation. The last thing that we need to talk about in this lecture is a little history of scientific methods. You've run across these words before, but we're going to make sure that you understand how these apply in the realm of physics. First off, the concept of a hypothesis. When we use a scientific method, researchers will begin with an educated guess about what they're going to find when they do the research. This educated guess is called a hypothesis. It's a guess. Then they test the hypothesis through research. There are two different types of conclusions that can be made based on research: theories and laws. The theory of relativity that Einstein's famous for it falls into the first category. It has been um, confirmed through observations, but it's not something that explains the pattern in nature. Someday it could be that that theory is proven wrong. A law, on the other hand, is an undeniable fact. Ohm's law that we encountered earlier in the lecture is always true. It'll never be proven wrong. It describes a pattern in nature. So, in general, laws are more ironclad than theories. Theories are built on the observations that we've made, but they might change in the future. Here's the problem set for section 1.1. It begins on page 4, and in the physics textbook, the problems are scattered throughout the section. I need you to do 1 through 17 all and submit them for evidence that you understood the content in this lecture. As always, you may ask me any questions that you want. If something doesn't make sense, please ask so that I can talk to you more about it and we can deal with any misunderstandings that might have occurred. See you next time.